Hello and welcome to this session of problem solving with the aid of a computer, and I hope by now you must be really familiar on how to use a computer to solve thermodynamics problems. Because in this problem we will tackle the problem in which there are two springs as shown in the figure. Two springs of the same spring constant are installed in a massless piston cylinder arrangement with the outside air at 100 kilopascal. If the piston is at the bottom, both the springs are relaxed and the second spring comes into contact when the volume is equal to 2 meter cubed. So, the second piston comes into contact when the volume is 2 meter cubed. Okay, no problem. Till then it is not engaged. The cylinder contains ammonia, a very useful industrial gas invented or synthesized during the First World War by Fritz Haber, the famous Haber-Bosch process. Okay. So, ammonia is at T1 equal to minus 2 degrees Celsius, x equal to 0.13 and initial volume equal to 1 meter cube. So, this initial volume is 1 meter cube. Okay, no problem. See, here we are showing this discs and all of thickness, but it's okay. You can take this, actually this is the 1 meter cube, and then when this expands and when the piston is like this, you reach the 2 meter cube. Okay. So, it is then when the second spring also comes into contact with the piston. Okay, no problem. So, when the piston is at the bottom, when V is equal to 0, the spring is sort of relaxed. There is no Kx by the spring. Okay, when the piston is at the bottom, the only pressure that acts is the 100 kilopascal. Why is this information needed? Because we do not have a reference state to find out how the spring is otherwise. See, the initial state is given somewhere at minus 2 degrees Celsius and x equal to 0.13 is state 1. But I do not know what the slope is. I do not know what the slope is because I do not have the spring constant. Okay, it can be anything. So, what determines the slope is the back reference state, because at V equal to 0, this pressure becomes 100 kilopascal. So, this actually tells me the slope, if I know the pressure at the first point, that is. Okay. So, what is going on? Okay, what is going on? It is heated now and the volume will rise. How long will the volume rise? Up until it reaches the second spring. Then at the second spring something will happen. What will happen? See, if this is the P internal times area, if there is only one spring, this K delta x, and it is P atmosphere for single spring. It is given that the same spring constant is there for the other spring as well. So, the moment the volume expands to 2 meter cube, so this point should correspond to a total volume of 2 meter cube. The moment we reach point 2, which is 2 meter cube, the second spring comes into picture, and thus we now have an additional K delta x, which is already, it was relaxed, the spring was relaxed. So, now you have an additional compression in this direction, and thus the P internal, so P internal before was P naught plus K delta x by A. But after the two springs come into contact, if there is a small change in volume, then both the springs will oppose that motion. So, then you have extra force. So, P naught plus twice k delta x by A. So, the slope of the line has become twice, because I can write P internal is equal to P naught plus 2 k delta V by A square. This delta V is obviously measured from the point where they hit the springs. So, from this point onwards, it will be at an increased slope, something like this. There is nothing but to say, but the effective spring constant has become twice. Okay. So, beyond this point, this equation will be valid. I hope this is clear. Till this point, this is the process. Okay. So, let us do some calculations and find out. So, we have been given T1 is equal to minus 2, x1 is equal to 0.13, and we have V total 1 is equal to 1. So, with the value of the temperature and the quality, we can find out the initial pressure. So, can you tell me what this pressure should be? This pressure should be identical to the saturation pressure, because it is inside the dome. Okay. All right. So, P1 is known, V1 is known. So, this point is known. What about point 2? So, we know that at point 2 the total volume becomes 2 meter cube, because point 2 I have defined as the point where the volume reaches 2 meter cubes in total, and this point VT2 is equal to 2. So, now can I find out the P2? Yes, I can, because the slope of this line is known. So, P2 minus 100 by 2 is equal to P1 minus 100 by 1. So, thus we obtain P2 equal to 100 plus twice P1 minus 100. So, this is equal to 2 P1 minus 100. So, let us put it down. P2 equal to 2 into P1 minus 100. So, thus we know what P2 is. All right. Now, what about state points 2 to 3? Okay. What about this? What about this process? What is the information that we have? So, the first question was, at what pressure will the piston touch the second spring? So, this is the pressure at which the piston will touch the second spring, and it is given that it is heated until the pressure reaches 1200 kilopascal. So, P3 is known. P3 is 1200 kilopascal. Okay. So, from points 2 to 3, this is the equation that we have. Essentially, when we write this down in terms of the actual process parameters, P3 should be equal to P2 plus 2 k by A square V3 minus V2. Okay. But how do we know? See, I mean, essentially this is the thing that we need to know. We need to know what V3 is. We know what V2 is, we know what P3 is, it is given, we know what P2 is. We just need to find out what V2 is. For that we need to know the spring constant. Can we find out the spring constant? Actually we can. Because when the spring is being compressed in the initial plot, when in the initial process, so if we write this equation down over here, it essentially says P1 equal to 100 plus 2k delta V by A square. Do we have the area of the piston? No, we don't have the area of the piston. Okay, no problem. Okay, but anyway, we don't need to do all this. We can simply do the following. We know that the slope is twice. And so P3 minus P2 by V3 minus V2 has twice the slope as this particular line segment. So this particular line segment has a slope which is twice this slope. Okay. So if I call this slope 2, this is slope 1. Slope 2 is equal to twice slope 1 as seen from this prefactor. So if we do this, we obtain this is equal to twice P1 minus 100 by V1 minus 0. So V1 was 1, and with the help of this we know V3 minus V2 is equal to P3 minus P2 by P1 minus 100 times 1 by 2, which implies V3 that we actually want is equal to V2 plus P3 minus P2 by P1 minus 100 times half. And alternately, the specific volume, see the mass is only known, so the specific volume cannot be used. So this is the way you have to find V3. So let's find out V3. So what is V total at 3? It is 2.844 meter cube. So this was 2 meter cube, this was 2 meter cube, and this final specific volume should correspond to something which is 2.844 meter cube. It should, I mean, there is not a specific volume, but we can divide by the mass. Okay. So what is asked? Let us see what is asked. We have been asked the temperature. Okay, the temperature we can find out. So to find out the temperature, we need to use two independent properties, one of which is the pressure, and the other we can find out by using the total volume and the mass. So the mass of the system is the mass of ammonia taken is. So let's find out first the mass of the total ammonia. So the specific volume at 1 is equal to volume ammonia at T equal to T1 and X equal to X1. So the mass is equal to the specific volume multiplied by the total volume. So once the mass is known, we can find the specific volume at point 3, which is equal to the total volume by the mass. For completeness, we will also find out the specific volume of point 2. This is equal to specific volume of 0.1 divided by 2 into 2, because the volume has doubled. If the volume has doubled, then we know the specific volume has also doubled because the mass is constant. Okay. Nothing sacrosanct about this step. Okay, temperatures. Let us find out the temperatures. T2 equal to temperature of ammonia at T equal to P2 and V equal to V2. Similarly, T3 will be the temperature ammonia, P equal to P3, V equal to V3. As a matter of fact, let us not define V2 like this, but let us do it the classical way, which is the total volume at 2 divided by the mass. I mean, it doesn't make any difference. So now we have the volume, the specific volume at 2 and the specific volume at 0.3, and V3 we have estimated using this equation. So V3 equal to V2 plus this, because we have made use of the fact that the slope is twice. Okay. So P3 minus P2 over here by P1 minus 100, the P3 minus P2 by V3 minus V2 is twice that of this particular slope. Okay. So let us see what the temperatures and all we obtain. Okay, this seems to be a small error, but let us see how we can debug this. So the pressure at point 2 is 696.7 degrees Celsius. The pressure is 696.7 kilopascal, but the temperature is showing something very absurd. Okay, let's open up the property plot and see what's going on. For ammonia, on the PV plot, let's draw which isotherm? Minus 2 degrees Celsius. Okay, so this is minus 2 degrees Celsius. And let us draw the initial point. So what is the initial point? On the x axis we have specific volume, and on the y axis we have the pressure. So this is the initial point. The initial point is running way far off, so there must be something wrong with the slope. So let us see if there is something wrong with the slope. This is how you have to debug the problem. So let us see what's wrong. So we have obtained the mass. Let's see what is wrong. What is the specific? So let's see if state 1 makes sense. State 1 makes sense, yes, 0.13, and the mass is also equal to 0.04174, because that is the specific volume, equal to the total volume divided by the specific volume. So the mass is equal to this. Okay. So let's see. All right, there we go. So mass is equal to 23.96 kg. So we had messed up a small formula. That's a very silly mistake, a very innocuous mistake. But anyway, it's good to see that even while we do this, we can make a small mistake. But you should not perform this kind of mistakes, and you should take motivation from this. Okay. And so what is the final temperature that we obtain? The final temperature is 50.44 degrees Celsius. Okay. So the final temperature is 50.44. Let's draw the schematic. So we have something like this going to this, and then with a higher slope, 1, 2, 3, and this is minus 2 degrees Celsius isotherm for ammonia. Point 2 was maybe like this, which is 13.65 degrees Celsius, and point 3 is 50.44 degrees Celsius. So these are the 3 points, and let's do the plot. Let's do the actual plot. Let's do property plot, ammonia on the PV, and let's have 2 more isotherms, 13.65 and 50.44. So with this, let's draw the overlay. On the x axis we have the volume, and on the y axis we have the pressure. There you go. It's a very Nice looking plot, just as we expected. It has a slope like this and then has a double slope. So what is the work done? What is the work done during the process? Now the last question is, find the final temperature, which is 50.44, and we have to find the total work done. What is the total work done? So total work done will be work done from 1 to 2 plus work done from 2 to 3, which is equal to half P1 plus P2 times V2 minus V1 plus half P3 plus P2 times V3 minus V2. Okay, so let's write it down in the computer. So the work done is equal to 56.24 kilojoule. So I hope it is clear how it is a sum of these two trapezoids, because the work, so this is specific volume, but anyway it is the volume enclosed by the curve in the P and total volume plot. Okay, I might as well have drawn this schematic in the total volume because the mass is 1. So it is this area. So this is the area of the trapezoid that I have just hatched, and this particular area, and this is that particular area. So these are two trapezoids, because when you have a linear function in P, the area that it sweeps is a trapezoid. This is one trapezoid, so area under the curve is the PdV. Okay, integral PdV is the area under the PV plot. So PV is going like this, essentially the area below this, which is a trapezoid, and hence it is this formula. It is very easy, and this has been covered in the theory class as well. So this area of trapezoid plus this area trapezoid gives you the total work done, which is 56.24. So in this particular problem, we have dealt with a problem in which there are two springs. So in the initial times, there is one delta V, P and delta V relationship, and beyond a certain point, when two springs attach, there is another P delta V relationship. So we have made use of one delta P relationship, not this one, but this one, initial time and the final time relationship. So from process 1 to 2, the pressure varies as this, and the reference state was this particular 0 point. Once that slope is known, the slope from point 2 to 3 is known to be twice this, because you are using the fact that now you have two springs. The fact that you have two springs increases the spring constant. So you have twice the slope, and because of that you can now refer directly that the slope from point 2 to 3 is twice the slope from point 2 to 1. So with this, and we have seen how the actual plot looks like, you should revisit this problem, you should do this problem again, because it involves slightly more concept than the previous problems, but nothing out of the extraordinary. You should be able to justify what you are doing by clearly understanding what the process is. It goes from point 1 to 2 and then 2 to 3, where there are two springs, 1 to 2 only one spring. For the single spring, you had a reference point at 0, where the spring was having no displacement. With that slope, you could do all the calculations in this problem. Okay, so with this note and with this slightly tricky problem, we finish here, and I will see you next time. Thank you.